Okay, hello everybody. So I'm going to continue to discuss in Chapter 6, Section 2 with you about how to solve these systems using our second technique that we've talked about, which is substitution. So let's get started. You can see in both of these equations, the first equation we have an x minus 3y equals negative 9, and then the second one is 5x minus 2y equals 7. As I said in the previous video, you always want to try to key in on a variable. If you have a variable that's by itself, that's going to be a good one to solve for. So you can see I highlighted that x right there. That x is by itself, so that is going to be really easy to solve for that x variable by simply adding 3y to both sides. So when I do that, I end up with x equals 3y minus 9. Okay, so we have now solved for x, and once I've solved for x, I can take all of this bit that x equals, this 3y minus 9, and I'm going to put it right in there in the other equation, in for x. So this whole part right here is going to get substituted into the other equation for x. And so let's do that. So the other equation is 5, and then x minus 2y equals 7. In place of the x that was here, I'm now going to write 3y minus 9. And you can see by substituting that in for the other equation, I now have a new equation that only has one variable. And then that is able to be solved for. So the first thing we're going to do is distribute the 5, and we'll get 15y minus 45 minus 2y is equal to 7. Now there are two like terms here, the 15y and the minus 2y. So those two like terms need to be combined. 15 minus 2 is 13. So we have 13y minus 45 is equal to 7. Now, once we've done that, we're going to go ahead and add 45 to both sides. And we'll be left with 13y is equal to 52. The last step, of course, would be to divide both sides by 13. And when I do that, I get y equals, nope, it's not going to be 3. It's going to be 4. Now, we have only done half of the problem, because if you recall, with these linear systems, and if I would draw a quick example, a linear system is going to be a line and then a number line, another line, and we're looking for the point at which they intersect. And remember, an ordered pair consists of an x and a y value. We have found the y value. We need to now find the x value. And the way that we're going to do that is we're going to substitute it back into one of any of these equations, right? Now, since we're looking for the x value, this one right here is already solved for x, so that makes the most sense to substitute back into. So I'm going to go ahead and utilize that equation, x equals 3, but in place of the y, I'm going to write a 4, just like that. And then once I do this, I can simply follow PEMDAS and solve for x. And as you can see, x is equal to 3. Now, once you have your x variable solved for and your y variable solved for, I would like you to write those as an ordered pair. Remember, ordered pairs are x, y. So this would be 3 and then 4. Okay, so the next equations, or the system of equations we're going to solve are these two. And so you can see this first one is already solved for y, which is really helpful because we won't have to do what we did up here on this equation. So since this one is already solved for y, we're going to be able to just directly substitute it in right there for that variable. And so if we do that, you can see in place of, let me highlight this, in place of the y, I'm going to put in 2x minus 4. So I'll have negative 6x plus 3, 2x minus 4 equals negative 12. Now I'm going to distribute this 3. And so once we distribute the 3, we have some like terms over here on the left-hand side that we're going to solve. So we have a negative 6x plus 6x. Now, those two things are going to cancel. They're going to go completely away. And what we're left with is negative 12 equals negative 12. So what we realize from this particular problem is all of the variables canceled away, and we were left with what is a true statement. So when that happens, what that means is this has an infinite number of solutions. Now, why would it have an infinite number of solutions? Well, if we go back and look at our notes, actually, it would have to be in 6.1, which we don't have that up right now. So let me just show you. There are three things that can happen whenever you graph a system. The two lines can intersect in one place. The two lines could be parallel, in which case they don't intersect, or the two lines could end up being the same line. And that's what we have here. And the reason why we know that that's what we have here is all of the variables went away and we were left with a true statement. Now, the last one we're going to take a look at is similar to the one before in that this is already solved for y. So we're going to put this 2x minus 3 right here in for x. So I'm going to have 2x and then minus 2x minus 3 equals 8. So I took this part, substituted it in for y right there. Now, we need to distribute this negative to both things. So we have 2x minus 2x plus 3 equals 8. And you can see this 2x and this 2x, negative 2x, are going to cancel, and we're just left with 3 equals 8. So this one is actually a false statement. And when you get a false statement, that means there is no solution. Okay. Now, if we scroll back up here for a second and look, that is going to be this instance right here, where the lines are parallel and they do not intersect. Therefore, there will not be a solution. So I forgot to label this last one. It should say infinite solutions. So please make sure that if you get the situation that we got for number 5, you do say infinite solutions. So if you get a just true statement, the variables go away, that's infinite solutions. And what that means is this. There's infinite solutions because they're the same line. If you get a false statement like 3 equals 8, that's false. That means there will be no solution. If we bring that line up here, you can see that belongs to this instance where the lines are parallel. So that's what I have for you today, guys. As always, if you have any questions, feel free to email me. Have a good day.